Hello calculus students. Today we're going to be looking at our last additional topic, kind of an addendum that we've already kind of pursued in class here and there, and that is being real confident about Riemann sum theory and how that relates to integrals. Just in terms of the theory and being able to do a couple example problems like that. So, technically, the exact area under a curve f, or the integral from a to b of f of x dx, is going to be taken or found when you take the limit as your subinterval size goes to 0, which means you take the limit as n approaches infinity of the Riemann sum, where this is the height of the rectangle, and we have a uniform width of the rectangle, which we can of course figure out by taking the edges that we want to find the area between, subtracting those, and dividing by how many rectangles we want to do. If we take that number of rectangles to infinity, we get an exact instead of an approximate area. We've been knowing that, I think we've known that for quite a while, but we want to look at the real particulars of how this works today. We're going to bring in some old school summation rules from Algebra 2 in order to facilitate that, okay? So I think the one thing that might not be super obvious is this. This specifies that you're going to be using a right-hand sum approximation technique. And that's the only thing you're going to see on the AP exam. You could, of course, do a left-hand sum, and it would work really similarly. The argument would be all the same. It's just you'd be referencing from the left side instead of, from the left side, instead of from the right side. Okay? So, clearly here we're using the right side because we're going A, which is the first thing, and then we're counting a certain number of subintervals away from that and taking the right-hand edge as our x value. Okay? So there you go. So let's use this technique to actually do an integral that, of course, we could come up with the exact value using the Fundamental Theorem of Calculus really quickly by going x to the 4th over 4 minus 3x squared and using the Fundamental Theorem part 1. Okay? So how do we do this with a Riemann sum? We're going to say, well, approximately. And of course, we could use any number of rectangles, but what we're most interested in now is an arbitrary number of rectangles. So we're going to develop an expression just based on n, which is going to be how many subintervals or how many rectangles we want to use, and then we can plug in whatever number we want, and the more we plug in for n, the closer it will get to perfect, right? Which of course we could compare to using the fundamental theorem. So if we just need to develop an expression solely in terms of n, that's what the AP exam on the latest versions is looking for you to be able to do, and I think it's really a good goal for them to have for us, so it's good. So, what do we want to do is dissect this. So b and a are pretty obvious, 3 and 0. And dx in approximate land is going to be
0.
What?
0, 0, 0, 0, 0.
Delta x, which for us is going to be what? What's our delta x going to be? 3 minus 0 over n, because we're just going to do an arbitrary number of subintervals, n subintervals. Okay? So there's delta x. So delta x is 3 over n. That's what we're going to stick right there. Then we need to figure out the height, or f of x. But before we do that, we have to figure out the expression form of the edges. So we're going to figure out what the places we're going to plug into look like in general first, which of course is x sub I. What do they look like in general for any specific node? Yeah? So x sub I is going to look like what? A plus I is the counter. Remember, the counter here is just telling you which one of those nodes in an arbitrary spot you're going to be at. So this is the counter, and then I've got to put my delta x right next to it. So there you go. X sub I is going to be I times 3 over n for this problem. Okay, so that's what we're going to plug in for x to find f of x, which is the height, so that we can go height times width. So we're going to say, all right, this is approximately equal to 3i over n cubed, right? Minus 6 times 3i over n to the first power. And then we've also got to do delta x, so we're going to have another 3 over n out here. And then what else do we need to put in there? The summation, right? So we're going to say approximately equal to, I need some space, the sum counting from 1 to n wherever we want to stop. So remember, the thing that might be a little foreign to you here is that I thing. Sometimes it's called k, right? On the AP exam problems we saw it is called k. It's just a counter. And getting used to counters is really important, especially if you're going to work with computers. Mr. Breckheisen probably knows all about that by now.
Oh, yeah.
So you really want to start thinking about this counter thing, but that's just saying from the first node to the second node to the third node. And since we're leaving this arbitrary n, we're saying, well, we'll develop an expression in terms of n, and then we get to choose what n is. If we make n infinity, it'll be exact. If we make n 10, it'll be eh. Make n 20, it'll be better. If we make n 40, it'll be better, and so forth. Okay? So we just need to simplify this guy now. So I'm going to say, okay, that's the summation I equals 1 to n. And I can simplify this by doing some basic algebra, right? So cube that, and you get what? 27i cubed over n cubed minus 18i over n. And then we could really even distribute this 3 through, right? Or isn't this 3 a constant? Think about what you know about sums and stuff. Can't we just pull that all the way out in front? I think I'm going to do that. I'm going to pull this 3 all the way out in front. And then this n I could just distribute here and here, can't I? So what's the next step after that? You could distribute the sum. I think sums distribute just like integrals distribute. So now if I distribute here, I'm going to pull out the 27 too. When I have like 81 sum from 1 to n of I cubed over n to the 4th. And then minus, if I distribute it there, 3 times 18. Can you guys help me out?
54.
54, thank you. So we'll have sum from 1 to n, I over n squared.
I squared.
And now you've got to think about this, and this is really useful for like Calc 3. Yeah? What are these variable based upon? What's the variable? What's changing and what's not? This sum goes from 1 to n in terms of I. I is the variable. In terms of I, n is just a constant. Yeah? So what can happen with this n to the 4th? It can be factored out of that sum because it's constant. This thing is operating in terms of I, not in terms of n. Yeah, it stops at the finite number n, but it's not based on n. So this is going to be I cubed, and over here we can do the same thing. And put n squared on the bottom and I. So all we need to know is how to express or come up with, simplify the sum of 1 to n of I cubed. That's just going to be 1 cubed plus 2 cubed plus 3 cubed plus 4 cubed up to an arbitrary n. And I believe in Algebra 2 I taught you guys those summation shortcuts. The first one that was real famous was developed by the little boy Gauss. It wasn't developed by Gauss, but I taught you that story where Gauss kind of figured it out. Real quick, I believe it goes n times n plus 1 over 2. This should bring you back in the Wayback Machine to something you learned in the past. And I don't think I ever made you guys memorize I cubed, but it's on your sheet. Can you guys tell me what it's at? It's on your sheet somewhere.
1 plus 1 over n squared, all of that squared.
For I cubed?
Yes.
I don't remember what it is either.
Yeah, 1 plus
It's
1
n.
over n.
Isn't it like n plus 1?
Oh, no,
It's
n
n
plus
times n plus 1 over 2.
That sounds right, yes. So it's just like this one, n times n plus 1 over 2, and this whole thing is squared?
Yeah.
So then this will be like a 4,
On the top of
and
it.
this will be squared. Okay, there you go. So there's the expression approximately based on Riemann sums. And the beautiful thing about this is that it's really easy for computers to use this kind of thing. This is how computers do things like Math 9 and so forth. You guys know what I'm saying. This is one of the ways that they work. Because all you have to do now is say, okay, that's like a Riemann sum estimate based on n, so I might call it like R sub n, right? And all I've got to do is pick how precise I want to be. And there's ways to decide how much error is going to be in there, which we'll start to look at in Calc 2. So if you want to be rough, you could pick like 10 and plug 10 in all these spots, and a computer would have no problem doing that, right? And you guys could put that in your calculator, no problem. If you choose instead n equals 20, your integral will be more accurate. If you choose 40, it'll be more accurate. If you choose 100, it'll be really accurate, probably. And if you choose something really big, it'll get so close that you won't even be able to tell the difference. And that's what machines do. So I'm not going to actually plug anything in there or try to simplify. I'm just going to go, that looks gross, but whatever. I can just plug into it and get a nice approximation. So what they did on that problem that we saw yesterday on the AP exam is gave you what? They gave us this. It was a much nicer, cleaner expression that they cleaned up, and it was just an easy integral. And they said, okay, take the limit as n approaches infinity, and you'll get the exact answer. So we could take the limit as n approaches infinity here, but we just need to simplify a little more, wouldn't we? I don't think I want to. Do you guys need me to? You just go n squared, n plus 1 squared, simplify this out, factor out all the constants, take the limit as n approaches infinity. It probably won't even be a hard limit, it's just got gross big numbers in it. So that's what they asked on that problem yesterday. Cool? Sweet. So you guys just follow the directions on your problems. Let's do one more. See if we can
Not just
figure it out.
27, because the top is going to be n to the 4th, the bottom's n to the 4th.
It might be. Don't you guys have a little bit more detail on that problem there? Have a look in your sheet.
Oh, it's 81/4 minus 27.
They simplified it a little bit more, but you can see that they got it one or two more steps after me, and then they took the limit, and they came out with the exact answer. So there you go, which is the same thing you'd get from the fundamental theorem. All right, let's look at one more problem. Okay, so here's another problem where we're going to estimate it and develop a Riemann sum approach, which then we can take the limit of to find the exact value instead of using the fundamental theorem of calculus. So, what are we going to have for our width delta x for this one?
3/n.
Same thing as last time, but coming from a different place. And we're going to have x sub I, the element we feed into f of x. It's going to be
1
a plus
3
counter
over n.
times delta x. So, a little bit different. It's going to be a little bit more of a pain because we've got the fun thing, which is most of the time the way it's going to be, right? So, we're going to say this is approximately equal to the sum from 1 to n. And if we don't want the approximate, we can just put equals and put what in front? The limit. We'll just do that later. So, it doesn't really matter. All right. So, I'm going to have x squared, which is going to be this stuff squared. That's going to be a little bit of a pain. Minus 4 of that stuff. Plus 2. And that's all got to be multiplied by 3 over n. So, last time, in order to talk about the theory more, which is mainly what we want to focus on here, I distributed that first. This time, let's be smarter. What will be smarter to do first here? Can I pull out the 3 right away? Can you pull out the n right away too? Yes. Because this is based on I, not based on n. And that's something that's really going to matter more and more as you go towards Calc 3, because in Calc 3 you have multidimensional stuff, and some integrals will be a dx, some will be dy, some will be dz, some will be dr for polar, some will be d theta or d phi for cylindrical coordinate systems, and you've always got to keep track. Anything that's not variable based on that can be factored out in cases, so big deal. This guy is just variable based on n. I can see that some people are still raising eyebrows about that. That's, I'm guessing, because this says n, right? But this just says where to stop. This says count from 1 up until that finite, solid, not variable stopping place. Okay? So the variable in here is I, not n. The n in here is just the stopping place on each one. That's all it is, which in other words means it's a constant.
Any number.
Exactly. We get to choose that constant, but we're going to choose one. It's not going to be variable. It's going to be our choice, which is solid, fixed. So we've got, that does not look like a 3. Looks like some kind of Chinese symbol. So I'm going to do that, and then I don't see anything else I can factor out, so I'm going to do some good old-fashioned expansion. So I'm going to have 1 squared is 1, plus 2 of those, that's going to be what, 6 I over n, thank you. And then this thing squared is going to be 9i squared over n squared, is that right?
Yeah.
And then this guy we're going to distribute, and we've still got a 2 chilling. Okay, so now I want to do anything else clever that I can. I've got a few like terms here, might as well put them together, right? So 3 over n is still chilling outside the sum.
3 minus 6i
And
over
we've
n.
got 3, and you said minus 6i over n, combining these. Is that what you did, Parker?
Yeah.
Those are like terms, I think you're right.
Oh, my bad.
Minus 6i over n.
So negative
So
1.
So we've got minus 4, so negative 1. Okay, good. So far we've taken care of this, this, and this. And we've also taken care of this and this. The only other thing left is this. What's the next step?
The n is constant, so you can
1, 2, 3
split
terms.
it apart.
Distribute the sum. Minus this one is going to be minus 3 over n. Distribute the last one. So here I'm going to have plus. I'm just going to pull this stuff out right away on this one just so you guys can think about it purely. I could have done that on all the other ones too, right? We clear on why this is n cubed?
Because you have to take out the 9i squared, or 9 over n squared.
And I could do that at the same time on this one. So if I go right here, that's going to be 18. The I is the variable. I can't take it out. This n is not, so it can't come out. And then here, that's all it is. So this is 3 over n. How does the sum of a constant work?
It is the constant.
It is constant.
No.
Isn't it just
This says add up negative 1 how many times?
n times?
N times. It says negative 1 plus negative 1 plus negative 1 plus negative 1 n times. So this is negative n. Or negative 1 times n. Yes?
Shouldn't the 6i then becomes I since you took out the 6?
Yeah, it is.
Yes. Thank you, Michaela. Forgot to erase it. Okay, then over here we have this constant based on n times this guy. This is Gauss's formula. We just did it a second ago. So put that in. And
Times n plus 1.
remember, it's this thing times that thing plus 1, the stopping point times the stopping point plus 1 over 2. And then over here, I think we did this one in Algebra 2 as well. I think it's 2n plus 1, n plus 1 over 6. Am I right? Look at your squared summation.
Times n
I think there's one thing missing.
times n.
Is it just times another n? For squared, you guys find it on your sheet. Make sure you're clear about where this is at. You've seen that before. So,
Don't you have to square the n and n plus 1?
where?
For the second part, when do you have to square that? Like the entire quantity?
If it's cubed, this
Okay.
is squared. Squared expansion. Single linear expansion. The other one was a cubic expansion. Okay, it's just the formula. So we've got a giant expression in terms of n. If we put 10 rectangles in there, we'll get an estimate for the integral. Let's try to do this one a little bit more and finish it up. So let's combine it as best we can at least.
When it's negative
So you can do this smarter or easier. You can see their examples are probably doing it a smarter way than me. But if we take the limit as n approaches infinity, limits distribute across as well, right? So I think that probably won't be too hard. Let's just try to do it without simplifying. What's the limit as n approaches infinity of this one?
negative 3.
Negative 3. Are we clear on that? Order of magnitude's the same, and you've got negative 3. What about this one? Let's think about order of magnitude and see if we can do it. N squared on top, n squared on bottom. So you just need the coefficient. What's on top?
9, negative 18.
Negative 18, and on bottom?
2.
2. So that's our answer. And then the limit as n approaches infinity over here. We've got cubed over cubed. You just got to be careful. So be careful about your distributing.
54 over 6
It's
is 9.
plus 9.
Is it 54 over 6? The coefficient of n cubed ends up being? So
You add
plus
that, it
9.
cancels.
So the answer is negative 3. So that's what we're supposed to get when we apply the fundamental theorem of calculus, right? Should we just check it real quick?
X
Integral. Yep, you're right. Thank you, Parker. 16. 8.
minus 1/3 minus 2 plus 2.
I'm not seeing a 3 yet. Let's see what happens. Oh, man. I don't want to do thirds. You suck thirds.
Negative 24.
64 minus 1 is 63 thirds.
Mm-hmm. And that is equal to
Negative 32 plus 2 is plus
That's
30.
equal to 21.
21.
63 thirds is 21. Yeah.
Negative 32.
8 minus 2 is...
So where's your 30 coming
8
from?
is negative 24. That's
I don't know.
negative-
Bad places. I'm doing bad math.
So subtract
It's
24.
8
Negative
minus
32.
So it's negative 24. So it's
All right,
21
let's just be
minus
careful.
24, which is negative
It's 63 thirds minus 24.
I'm going to be careful. So this is minus... I was doing a different order than you guys. So minus 24, and then we've got...
No,
That's
the-
gone,
that's
right?
gone.
Yeah.
You already took care of the other one there too, so.
Negative 30.
Yes! Success!